Gérard Mourou,
Gérard Mourou, Premio Nobel
Nobel
2018
Prize
per la
2018 for
Ringraziamo
physics.
moltissimo di essere qui.
Thank you very much for being here.
E devo dire che
And
da
I
soli
have
non
to
ce
say
l'avremmo
that we
fatta.
would have never
Abbiamo
managed it
avuto
on
un
our
grandissimo aiuto,
own.
come tutti gli
We've
anni,
had a
dall'ambasciata
great
di
help
Francia.
from
L'ambasciata
the
di Francia ad aiutarci
Embassy
a
of
tenerlo
France.
qui con noi.
They helped
Quindi
us
questo
to get
applauso va
him
naturalmente anche
here
a
with
questi
us,
nostri amici.
so a round of applause for the Embassy of France.
Io ho cercato lungamente a casa,
I
ma non sono riuscito a trovare
tried to
un metro
find at
laser,
home
perché
a
è un
laser
oggetto
meter,
che
but
porto
I
spesso
failed to
nelle
find one.
scuole quando
It's
devo
an object
parlare ai
I
ragazzi, per
often
far vedere
take to
una
schools to
invenzione
show
del
one of
laser.
the many
Curioso, perché noi
applications
pensiamo
of
che misura
lasers,
una distanza di
and it
60,
can measure
80
up to
metri
60,
con la
80
precisione di
meter
1 millimetro.
with the precision and accuracy of 1 millimeter, and I find that this
Ho trovato un altro
is
laser
wonderful.
che
But I
invece per
found
indicare le
another laser beam which I use to indicate on the stars on the ceiling. I'm trying not to point it on the audience, but on the walls, and it's something that we can carry with us, just like pointers that we use for PowerPoint presentations. When lasers were invented, someone said that it was a wonderful solution, but it was still seeking for a problem. Apparently, lasers were technically and scientifically something interesting, but it would never have had any practical use. Obviously, this has been disproved, and in fact, it was quite the opposite. We use lasers in every side of our life. So, for example, compact disc readers or DVD readers. So if you see movies or you listen to music, it's because there is a laser beam that reads it. But it has also been used for other things. If you have a much stronger laser beam than this, if you're pointing it to a satellite that has a radio reflector, we can measure the position of continents. And if continents move, as they do, by a few centimeters a year after a few years of measurements, with these laser beams, we can know exactly how much they've moved by and which direction. And this is very important for geography and geophysics. Many of us have also enjoyed the benefits of laser beams in surgery. And if you can also, if you've been involved in metal cutting, you know the advantages of cutting with a laser beam. This has been an enormous advantage, and great scientists have contributed to it since the 1960s. About 20 years have received the Nobel Prize for work that is related to the laser beam. Very often, the word laser is not included in the prize, because in the Nobel Prize, you only quote the invention the first time, while you then quote the work that has been done on it. And here we have Gérard Mourou, who is with us and who is responsible for one of the great people. And I'll tell you what he did in 2 words. He took a laser beam and then he dilated it and compressed it. This happens in 1 billionth of seconds, and this time is unimaginably short for us, and it is the time that required for an electron to rotate around the nucleus. So we're very close to the chemical reactions. And this light, this laser light, which is called extreme light, is 1,000 times more powerful than the most powerful laser lights. This is one of the things that Gérard Mourou had studied, and he's here with us this evening, and we really are very curious to hear him speak this evening. Thank you very much.
Thank you. Merci.
Thank you.
Merci beaucoup.
Thank you very much.
C'est pour moi. OK. Well, buonasera.
Good evening.
A tutti.
Good evening to you all.
È un piacere
It is a pleasure
essere
to be here
a Torino
in Turin
con
with
un pubblico
an audience
così numeroso.
which is so big. Thank you very much.
And you know, I have to say, en français.
In French, I must now speak French. He was telling me that for them, working in this, English is better than their mother tongue sometimes, but in fact, we are pleased to hear him speak in French. It is my pleasure to be here because I come from the other side of the mountains. I am originally from Albertville in France, not very far from here. I'm going to be talking to you about what led to me have the Nobel Prize awarded to me in 2018. Probably you know about it, but the Nobel Prize is announced the first Tuesday in October, towards midday. And on that day, I was going off to the swimming pool, as I do every day, and my secretary ran after me and said, you have a phone call from a foreign country. I took the phone, and the person who was on the other end of the call introduced themselves as Göran Larsson, the chairman of the Committee of Physics for the Nobel Prize selection. And he told me that that I was going to be the Nobel laureate in physics for 2018. He also told me that I was going to be sharing it with my student, Donna Strickland. I was extremely proud, pleased that I was going to be sharing this prize with my student. In fact, there have been 200 men before me who have been awarded the Nobel Prize in Physics, but only 2 women. Only 2 women had been awarded the Nobel Prize before Donna Strickland. So I was overwhelmed because I was being awarded the Nobel Prize, but also my student was also going to be recognized. The chairman asked me, I take it that you accept the Nobel Prize. And I said, yes.
Voilà. Donc,
So,
je vais vous parler
I am going to be talking to you about of my passion for extreme light. First of all, I will be talking about light in itself, and that is clearly the light that is something that the electric bulb will give. The photons that are emitted by this bulb come in all colors, are multicolored. They spread in all directions, and this is a laser. You see that it's completely different It's very different because the beam consists of very few wavelengths. So I'm going to make a comparison between the two types of light. The first type of light is what we call an incoherent light, which could be compared to a group of marathon runners. All the runners are dressed in different colors. They are running at different speeds, and they don't really know each other. Unlike the incoherent light, this is more like a laser light, a coherent light, and in this case, all the soldiers that are part of the march are dressed in the same way, and they are marching at the same speed, with the same gait. And if you know the position of one of the soldiers, you in fact are aware of the position of all the soldiers. This is more like a laser light. A laser can emit very short bursts of light. These can vary milliseconds, microseconds, nanoseconds, picoseconds, femtoseconds, and now attoseconds. In particular, we're going to be working now with the lasers that emit in femtoseconds, 10 to the power of minus 15, which is 1 millionth of a billionth of seconds. Before describing the applications of this femtosecond lasers, I would like to introduce Ted or Theodore Mayman, the first scientist who got a laser beam to actually work. The light first appeared 14 billion years ago, but it was always the incoherent light. Ted Mayman, in May, the 16th of May, 1960, showed for the first time the production of light, of coherent light. This was an enormous step forward, and we didn't know what level of applications there would be, but there have been many more than what we could have even imagined then. I'm going to be talking about extreme light, and I shall explain why this light is very special. It's so important. Extreme light, as I was saying, has impulse duration of a femtosecond, 10 to the power of minus 15. It's so short that throughout its duration, it does not move, but by a few microns at the size of a red blood cell. Why? Well, because you can produce very, very short pulses, even though the energy that it has is very weak, sort of a joule. A joule is a very weak measure of energy. It's the energy that you need to increase the temperature by of the volume by 1 cubic centimeter by 1 degree. That's the definition. But if you produce it, if you generate it in a femtosecond, then you have a pulse which has the power of a petawatt. Petawatt or petawatt is the equivalent of 1 million gigawatts. This is a nuclear power plant that produces energy. Roughly, these nuclear power stations produce about 1 gigawatt. And a petawatt, to produce that, you need 1 million of these. Furthermore, a petawatt is 1,000 times the total power of the global grid throughout the world. So it's really a lot of energy. And of course, it is produced in a femtosecond. Now, let us see that extraordinary power. You can focus it on an order of magnitude which is 1 micrometer. Well, one of your hairs has a size of 50 microns. So if you focus this pulse on 1 micron, you have a radiation pressure which is enormous, about 10 million Eiffel Towers on 1 finger. So this is just to give you an idea of extreme light. And now I'm going to move on to possible uses. Extreme light is able, the laser, extreme light laser, is able to produce pulses which, as I mentioned, is very important and generate very high temperatures and also pressure and also the very important level of acceleration. It is a universal source of particles, high energy particles and radiation. This is why we were awarded the Nobel Prize, me and Donna Strickland. I'm now going to describe the progression of the laser intensity as from when Theodore Maiman produced the first laser systems, pulses. In 1960, that's where we were. Roughly, that was about 10 to the power of 10. You can see it here. Then it grew very rapidly, and the power and intensity increased, and following that there was a sort of plateau for 20 years where the intensity did not grow. The reason why it couldn't grow is that it was it damaged the optical materials that were used to generate it, the materials in the laser, which was like a boundary point, and we couldn't go any further. And at that point, in 85, we showed or developed this notion of chirped pulse amplification, CPA. Thereafter, laser intensity increased by several orders of magnitude, especially if you consider that initially the intensity was the equivalent of a fly, so to speak. Now it is as big or as strong as an elephant. Of course, when we change the intensity, then you penetrate, you cross the different boundaries and enter a new area in physics, which is what I'm going to be describing. Before talking about the applications or uses, I shall describe the birth of this technique. There I was, skiing with my wife, Marcel, and you know, when you're skiing, and a lot of people I expect in Turin go skiing, well, you take the chairlift, and if the day is beautiful, you sit there, you dream, you daydream, the landscape is beautiful, the trees are beautiful, and it is really very promising, and you can always get ideas then, and that is where I thought the method out. That is to say, how we could go beyond the plateau that we seemed to be stuck in. And I said to Marcel, my wife, it's so important. I said, I must go back to the lab now. At the time, I was in the US when this happened. So at that point, when we got to the tip of the mountain, where the chairlift stopped, I went down, I skied down. I went to my car, and I went back to the lab. And Marcel went off with our friends who were with us and went back to ski. Now, I went to the lab and I said to the students, or the people there, some of my students were working there, I said, stop whatever you're doing, because what we're going to do is this. And I described or illustrated the notion of CPA. We're going to take a pulse, a very short light pulse. At the time, it was 1 picosecond, with only a few optical cycles. And since it was very short, it contained a very high number of frequencies. Then I said, we're going to take the system like a network, a diffraction network, we're going to disperse light, the light which this pulse is made up of, and as you can see, each wavelength is going to go along a path which can be long or short. With a short one, you can now end up with a long one. This means that the intensity has decreased by the fact that it has been unraveled, it has been stretched. That moment, we had the energy which hadn't changed, but at that moment, the intensity could no longer damage the materials of the machinery and the instruments, which meant that the pulse was stretched, but it was stretched by a factor of 1,000 initially. Now it's about 1 million. So you can extract the energy from 1,000 to 1 million times better. So now we have these pulses which are stretched, and you have to recompress it with the same system but organized in a different manner, and the pulse is repositioned and giving it its initial duration. I think it was a picosecond or just below that. Now, at this point, the pulse is enormous. And currently, as I was saying, if the one where we started with had the weight of a fly, the outcome is as heavy as an elephant, which is really a big change. Now, we're going to be talking about the various applications. We're going to be talking about the applications, first of all, at levels of intensity which are relatively limited. And we shall see that there are many applications here. Then we will move to what is here in a green, and there the light and matter behave in a different way. And then if you increase the pulse even further, you get the yellow area where the intensity is so great that we're going to be able to boil a vacuum. What do I mean by that? We are going to be able to create matter from light and vacuum. Now let's go back to the lower levels. And we're going to start with the implementation which is called micromachining, which is fine in Turin because there are a lot of uses you can have of it here. In here, I'm going to show you that the extreme pulses, the ones in femtoseconds, have a lot of uses because they do not generate any side effects or damage. Here you can see a pulse which is relatively long, and you see that in the course of it, that while it is absorbed by the material, at that point all the volume around the focal point is going to heat up, and the heat is going to spread, and it will leave a hole, quite a large, quite a sizable one. If we use shorter pulses, then you will observe that you heat the material, the target material, less, and the heating is limited to a smaller area. But if we now take some femtosecond pulses, then in that case they're very, very short, and the volume which is affected is very small, and heat can no longer heat the surrounding area. And there is what we call a focal impact. You will observe that in this case there is no further damage. For example, if you use a long pulse, which is a nanosecond, you see, if you want to make a hole in a metal, well, you see it forms rather a large crater. On the other hand, if you drill with very short pulses, femtoseconds, then you can see that the holes are absolutely perfect, without any side effects or side damages, and that they can also be used with very different materials like ceramic or metal or glass. In a minute, you will see also it can be used with a cornea, with the eye. It is very, very, very important use. Another thing now, which is really outstanding with laser pulses, that is that you can focus. If you focus the laser on a material which is transparent, well, at that point, at the focal point, where you have the greatest intensity, where you have the greatest electric field, you're going to create a cavity. And this cavity is small, and if you do this, you can create a flap. This is exactly what is used for the cornea. We know that very many people, for example, want to get rid of their glasses, and if people are short-sighted or nearsighted, they'd like to see without using glasses. This is why this is the ideal instrument to change the curve of the cornea. And now there are 24 million operations, millions and millions of people who have undergone this type of surgery thanks to the femtosecond laser. I have to say that you can see here the difference if you have a pig cornea, and you see what happens if you use them to produce a flap with impulses that are 300 femtoseconds, but if you do it with 50 picoseconds, which is short but not the same, it's not short enough, and that's the result you can see on the right, on the far right. Now I'm going to tell you a story about how this happened. At the time, you know, I'm a physicist. I am not an eye specialist, but one of my students in the lab, in fine-tuning a laser, received a laser beam in his eye. It was a serious matter. The student came to my office to see me and excused himself for the accident. And he excused himself because he knew that in the US, You could even have the lab closed down because of an accident like that. So I took him to the hospital, and at the hospital, a doctor looked at my student and said, and was absolutely gobsmacked. He said, "It's really extraordinary, it's exceptional. What you've done is you've received your laser beam in the eye, but what is extraordinary is..." What is extraordinary, we all asked. He said, "Because now it's perfect. Your retina is perfect, and therefore we realized there and then that there was a very important application in ophthalmology for lasers for using femtoseconds." The Michigan University gave us some funds for us to continue this type of research project in ophthalmology with femtoseconds. And now there are lots of systems like this in the world. We had carry out LASIK, or you can use it also for a graft of the cornea, and for a large number of different uses. And now we were here, we were in the purple area, we're going to now increase in intensity, and we're going to see a completely different type of application. When you're in the green area, intensity for the first time, the intensity is such that the electrons that oscillate around the nucleus, the atom, those electrons at this point, because of the effect of the electric field, become relativist. That is to say, they have a relativist speed, which means that their mass is going to change, and also other properties are going to change. So really this domain is going to be completely new. And you will see that a very beautiful application is, or very interesting, is the use of laser pulses for the acceleration of particles. It's very, very effective. If we increase intensity even further, we will accelerate not electrons but protons, which are 2,000 times heavier. And therefore, we need more intensity. And at that point, proton acceleration has very many uses, both in the science of materials, medicine, and also for the environment, because we're going to use them for the treatment of nuclear waste. If we increase it even more, if we increase the pulse even more, at that point, the light is so intense that it interacts with the vacuum. And the vacuum is something which is not empty at all. The vacuum is made up of particles and antiparticles, and the laser pulse is so big that it is going to separate particles from the antimatter. So at that point, from the vacuum, we will produce matter. There's a light materialization process. This is really a very important use that we would like to do. We're not really yet there, but I think that in a few years we will be. Now, let us talk about the uses of extreme light in the medical field, environmental field, and space. To accelerate particles with a laser, we are going to create what happens in the sea with waves, and we're going to try and do the same thing, which the same as this surfer surfing the waves. What we're going to do is that in a gas jet, we're going to send a very strong pulse. We ionize the material and we will create a wave, a plasma wave, which you can see on the right. Now, if the electrons fall on this wave, they're going to be propagated. They're going to be taken just like the surfer. They're going to be surfing the wave, and they're going to accelerate at the speed of light. That's the speed. And what is noticeable is that the acceleration which we will obtain is very effective and very, very much more effective than the techniques that have been used so far. To give you an idea, we're currently able to produce particles of a Geiger electron volt by centimeter. That is to say, on a centimeter, we have a Geiger electron volt. To give you an idea of this, this is outstanding, because currently, if you wish to produce a Geiger electron volt, you have to use a system which is like this, that is hundreds of meters. This is the Soleil synchrotron, which is near Paris. So it is very important because accelerators, there are many of them, but there are many used in different levels and different types of implementation. For example, here you have the Large Hadron Collider accelerator, which is in CERN. We use the traditional method of microwave cavities, and this is why we have 1 Geiger electron volt per centimeter. Therefore, this means that for a tera electron volt, you need tens of kilometers. There are 27 in this case. But if you use the laser wave field X-ray, you should really have cavities which are probably... No, let me reword that. You have to have systems of acceleration of about 100 meters. And currently, we're working on systems that do not use gases but solids. And there we are expecting to have even stronger acceleration. And we have a centimeter, that is to say, you can reduce the size and have it on a finger. This is to give you an idea of what can be done. And now I'm going to be talking about the various uses in the medical field, because in a medical field you have lots of needs that have to be met to produce protons, proton therapy, but also to produce radionuclides for nuclear treatment or therapy, and also for diagnosis or diagnostic instruments. You need accelerators to produce all these particles. Now I'm going to be basically moving on to talk about proton therapy. Proton therapy currently could be used instead of electrons and X-rays. The issue that we have with the electron therapy and X-rays is that if you have a cancer which is located amongst other tissues, healthy tissues, then you focus clearly the beam of the X-ray or an electrons on the cancer to burn it out, so to speak. But, of course, the healthy tissues that are in front of the cancer will be affected. This is why it's not the ideal solution. While with protons, protons can be accelerated and can hit the cancer, and you can stop them exactly where you want them to be according to the energy that they have. And you do this destroying less the tissues that are in front of it. Another use for protons is, of course, what I could term neutralization or mitigation of nuclear waste using CPA. One way of doing it is to transform them or transmute them, because as I was saying, you can generate energy particles that are enough, and in the production of energy, you also produce what we call minor attitudes, which are in fact the ones which cause the greatest damage. There are four: neptunium, americium, curium, plutonium. These elements are very important because they're very, very long-lived. So very difficult to get rid of these products. But if we have high-energy neutrons, at that point you can fission the nucleus of these elements, and the resulting ones have about 10 minutes half-life, days, hours. So much, much shorter than what we have normally. Now, there is another application of extreme light, or for extreme light, or more exactly, the lasers that we're currently developing for extreme light, and that is the cleansing of space. That is to say, eliminating the orbital debris. You know that ever since the space era that started in 1957 with the Sputnik, ever since then, we have sent into space the equivalent of 4 Eiffel Towers, 28,000 tons of material. And by doing that, we've also produced enormous amounts of debris. The debris can be cubic meter, size of a washing machine, but they can also be very small, centimeter or below. But they're extremely dangerous because they propagate at a speed which is 10 times the fastest bullet. The best is here to come, as we say. We can now progress. Now, I'm just going to show you something about the Nobel ceremony. What has happened, or what happens after the phone call. The Nobel Prize is awarded the 10th of December. And the 10th of December, what do we do? Each Nobel laureate has to present their lecture, has to give their lecture. There's me doing it, and here I am with Donna, my former student, and the chairperson. And what we have to do is that we have to learn how to receive the Nobel Prize. Here, for instance, it takes about a morning to learn. So here there is a person who acts as if they were the king and shows me how the prize is awarded physically. And I have to learn how to say, how I have to greet the king and how to do it, when to do it, what I have to say. And that is something that you learn just before. Here I am with Donna. We're looking at the others who are learning. We were having fun then. Before the Nobel Prize, that's my wife, Marcel, and Donna, who are doing my bow tie up. And here's the ceremony, which is really very impressive, very. Here you can see the royal family and the 10 Nobel Prizes there. So, physics, chemistry, medicine, and economics, or economy. But physics is number one, obviously. That is why we were there. And there you see the royal family, the members of the jury. Here you can see me being awarded the prize. Really very impressive there. I was very happy, obviously. And all my colleagues, all my co-laureates received their prize. So here you have physics. There were 3 of us, and the third person was unable to come because he was 96. Here you have chemistry laureates, medicine, and lastly, economics or economy, but it's economics. Now here, I'm congratulated by Marcel, my wife. She was very happy. She was very pleased because she was wearing a dress that was lent by Dior. She was very happy. Following that, there is a banquet, an enormous banquet, with 1,500 people. And here you can see the royal table. It is at the center, and all the Nobel laureates are sitting there. So here you see Donna Strickland sitting next to the king, obviously, because, as I said, it's physics, and she's a woman, so she's sitting next to the king, and I'm sitting in between the Queen and Princess Sophia. Following that, and that is the moment which I found the most moving, because all the other things were moving too, but this was, because the others were glamorous, but this was just moving. It's the last thing that you do when you receive a Nobel Prize, and when you're awarded it, on the last day, you're taken to an office, and they come with some books, some exercise book, 1, 2, and these are where all the signatures of the previous Nobel laureates, and they ask you to sign too. So it's really something that touched me. For my wife and I must say that I like to show this slide because I would like to acknowledge my wife, who stood by me for 52 years. So thank you, Marcel.
Voilà.